In this example, I need to find the exact value of cosine squared 67.5 degrees minus sine squared 67.5 degrees. As the problem says exact value, this means don't use your calculator. I need to use my unit circle over here. But unfortunately, 67.5 degrees is not on my unit circle. So I'm going to have to use my knowledge of identities to rewrite this expression in terms of angles that are on my unit circle. Now be careful, this sign is a minus. If this had been a plus, remember cosine squared A plus sine squared A equals 1. But because this is a minus, the answer is not that simple. It's not going to equal 1. So hopefully this 67.5, the 0.5 indicates maybe dividing by 2. So what happens if I multiply that angle by 2? So 2 times 67.5 degrees is 135 degrees. And is that on the unit circle? Yes, it is right here. Now I'm going to show you two different methods for solving this problem, and the most efficient method surprisingly doesn't involve a half angle identity, but involves double angle identities. And here I have the double angle identities for sine, cosine, and tangent, and I need to compare those to my given expression of cosine squared 67.5 degrees minus sine squared 67.5 degrees. Do any of these have this same format? Yes, if you look, the cosine of 2a, one of the ways of writing it is cosine squared a minus sine squared a. So in this problem, I know that a is going to equal 67.5 degrees. So 2a is going to equal 135 degrees. So my given expression here, using this identity over here, can be written as the cosine of 2 times 67.5 degrees. So that is equal to the cosine of 135 degrees. And using the unit circle, what's the cosine of 135 degrees? Is the x-coordinate of this point. So it's negative the square root of 2 over 2. So the exact value of my expression is negative the square root of 2 over 2. Now in the second method, I'm going to use the identity for the half angle formulas for the sine and the cosine function. And in this case, my a over 2 is going to equal my 67.5 degrees. And so multiplying both sides by 2, I get a equals 135 degrees. So now all I have to do is substitute this for the cosine of 67.5 degrees. Remember, I'm going to have to square it, so put parentheses. And then I have plus or minus the square root of 1 plus the cosine of a. Well, a in this case is 135 degrees, all divided by 2. And remember, I'm squaring that, minus sine squared 67.5 degrees. So I have to square this expression. So it's plus or minus the square root of 1 minus the cosine of 135 degrees, all divided by 2. And don't forget, I have to square that expression because the sine and the cosine are squared here. Well, this looks like a big mess, but luckily when I square this square root, they undo each other. So I get 1 plus the cosine of 135 degrees divided by 2, minus, you must put parentheses, square this expression, I get 1 minus the cosine of 135 degrees divided by 2. Now my denominators are the same, so I have a common denominator of 2, and in my numerator I have 1 plus the cosine of 135 degrees. Distribute in the negative, which means change both of these signs, so I'm going to get minus 1 and plus the cosine of 135 degrees. And 1 minus 1, those add up to 0. So I get the cosine of 135 degrees plus the cosine of 135 degrees, which is 2 times the cosine of 135 degrees divided by 2. These 2's reduce, so my expression equals the cosine of 135 degrees. And looking on the unit circle, here's 135 degrees. The x-coordinate is negative the square root of 2 over 2. Did I get the same answer by the second method? Yes. Now, was this method more complicated than the first method I looked at? Yes. Now, if you happen to see this more efficient first method, great. But if you use the second method, it is equally correct. It just takes a little longer to complete.